This portion of the tutorial is problem 6.2 on page 117 in the SPSS for Intermediate Statistics textbook. This portion focuses on how to correct multicollinearity using simultaneous regression. On page 117 in your text, you can see actually 117 through 118, you can see the directions for what needs to be done if you need to see it in writing. And here's a video to show you what it looks like when putting it into your SPSS. In the previous problem, we looked at the data which suggested that there was possible collinearity issues. So problem 6.2 will ask us to run a simultaneous regression correcting multicollinearity. In the previous problem, if you will recall, we ran mother's education and father's education as two separate variables. In this problem, we will recompute using the multiple regression, but we will combine these two variables, or we will use the combined variable for parents' education. In addition to this, we will recompute after we omit competence and pleasure. If you will refer to page 117, there's a good explanation for why we're eliminating those two variables and why we are making the combination of parents' education. We will begin by creating a matrix scatter plot. In order to do this, we will go to Graphs, and from the drop-down menu, we will choose Legacy Dialogues, and from that drop-down, we will choose Scatter Dot. Make sure that we highlight Matrix Scatter, Define. We will now move our matrix variables into the matrix box. In this case, we want to move math achievement, grades, parents' education, which is the new variable, and gender. We will click on the options box and check to be sure that excluded cases list-wise is checked. There we go. And then we hit continue and we click OK. And you notice that we have a scatter plot like this. We're not quite finished. Now we're going to run the regression analysis. And in order to do that, we will go into Analyze. We will select Regression. We're going to do a linear regression. The linear regression window will open. Here we will select our dependent variable, which is math achievement. And our independent variables are motivation, grades in high school, parents' education, and gender. All right, we want to make sure that method enter is selected. We click on statistics. In this case, we want to make sure that estimates is clicked under regression coefficients. And we want to click model fit. we want descriptives, and we want collinearity diagnostics. Continue. And then we're going to add a plot to this as well. And the way we do that is we're going to select residual to go in the y-axis and to go in the x-axis. The plot will enable us to check the assumption that the predictors and residual are uncorrelated. Okay, so now we're finished. We're ready to click OK. And we get a new set of data, as well as our scatter plot for the second set of data. Now, we want to help improve the readability of the scatter plot. So by double clicking, we can edit the chart. And what we're going to do is we're going to add a y-axis reference line. And the way we do that is by going into Options, y-axis reference line, and we want to set it at 0 on the y-axis. So in the position, we want to change that to 0. And we want to apply that and close. And that updates the scatter plot. It's supposed to anyway. Let's try that again. Going to double click. It's there. There it goes. All right, and that is the end of the analysis. In front of you, you see the scatter plot matrix, and it shows that the independent variables are generally linearly related to dependent variable of math achievement, meeting the assumption. One should check the matrix scatter plots to see if there are curvy linear relationships. You'll notice everything seems to be in a linear fashion, straight across, up and down. There are no curves back and forth. Oops. Way ahead of myself here, guys. Sorry, so everything is in a linear fashion, which proves that there is linear, it's generally linearly related to the dependent variable of math achievement. In this example, none of the dot patterns are closer to the curve than a straight line or to no pattern at all. If the variables had not met this assumption, we would have transformed them, aggregated them some, or eliminated some independent variables so that we could get a clean scatter plot like the one we see in front of us. The next piece of output is the correlations. The correlation table shows that all predictors are significantly related to math achievement. There are only low to moderate relationships among the 4 predictor variables. This is good because it suggests that collinearity is not high, a condition of multiple regression. The next set of outputs is the model summary and the ANOVA output. The model summary table gives the R, which is 0.68, and the adjusted R, which is 0.43, as you see I've circled. Thus, this model predicts 43% of the variance in math achievement. If we want to compare this model to that in problem 6.1, we use the adjusted R-square to see which model is explaining more of the variance in the dependent variable. Interestingly, this model is predicting more, 43% versus the 36% we saw in 6.1 of the variance in math achievement. As can be seen from the ANOVA table, The model of motivation, grades in high school, parents' education, and gender significantly predicts math achievement. The next output you see is the coefficients table. After checking the matrix scatter plot and the residual scatter plot, the next important condition of multiple regression is to check the tolerance and the VIF values in the coefficients table. In this example, we do not need to worry about multicollinearity. I can't even say the word, multicollinearity, because the tolerance values are all close to 1. In the SIG column of the table, we can see that now all of the predictors are significantly contributing to the equation, and the betas are higher than in problem 6.1. So each of the variables has increased the amount of unique variance that it is explaining. The outputs you see here are the collinearity diagnostics and scatter plot. Other conditions and assumptions are demonstrated in these two tables. Other assumptions are checked in the residual scatter plot at the end of the output, which indicates the errors are approximately normally distributed. The variances of the residuals are constant, and the residual is relatively uncorrelated with the linear combination of predictors. Notice here, if the dots created a pattern, this would indicate the residuals are not normally distributed. The residual is correlated with the independent variables and/or the variances of the residuals are not constant. All right, now we need to figure out how do we put all this data into APA format. Basically, what I've done is taken the text from page 124 and formatted it correctly according to APA guidelines. The results section of your work should be double-spaced. The tables should be placed beneath your work. Notice that within the work I did not reference where the tables were located. I didn't say table below or anything like that. So everything is just referencing the table number, and that's how your APA formatting should be. Something I noticed in our work this week was that some of us were not using a double space formatting in our tables. One thing I can say about SPSS is that the tables are actually in APA format, even though the examples of the outputs are not correct according to APA. One example is when we talk about the R square. In APA, we have to actually write it out as R square. And if you'll notice on page 124, they spell out the word squared. So just some minor things that are minor differences, but according to APA would be incorrect. All right, I hope this tutorial has been helpful. I know it's been lengthy, so I appreciate it if you're still keeping up with me. And I challenge you all to say the word multicollinearity about 30 times. Have a great week.